this is John Whitaker for the Mathematical Analysis 1 class, and this is our 25th video lecture. And I had thought that maybe I would start today reviewing just a little bit of what I had done last time, having to do with those subsequential limit sets and the supremum of them. But I reviewed the tape, and it looks okay to me. So we're going to move on to Chapter 4, which is the last chapter that we'll be covering. And we're going to, that chapter mainly deals with continuity of functions, but it starts off with limits of functions. That's what we're going to start off with. So here's the definition for a limit of a function. We let x and y be metric spaces. Suppose that E is some subset of X. F maps E into Y, and P is a limit point of E. Then we write f of x, there's a little x here, goes to Q as x goes to P, or the limit as x goes to P of f of x equals to Q if there exists a Q element of y such that for each epsilon greater than 0, there exists a delta greater than 0 such that that the distance in y of f of x the distance between f of x and Q will be less than epsilon. Okay. That distance between f of x and Q will be less than epsilon for all points x in E such that, or for which, 0 is less than the metric on x between x and P is less than delta. And I should say where d sub x, x, y, I'll just write it down as d sub x and d sub y are the metrics on x and y respectively. So pictorially for a limit, here's what we're going to look at. This is the idea. We got this space x. There's x. And this is E. And P is some limit point, let's say. And it doesn't have to be an E, but I've drawn it to E. Okay. And this is y here. Okay, there's y. And so here's what's going to happen. What we're saying is, if you look at Q over here. So here's Q. And you put some ball by it, epsilon, okay? The epsilon neighborhood. Then you give me that epsilon neighborhood. And what happens is that there is some, if if you will, some delta neighborhood of P, such that all the points within that delta neighborhood of P are sent to points within this epsilon neighborhood of Q. So maybe it gets sent here. Okay? So that's what's happening by F. And I want to tell you is that this is true for every point in this neighborhood except possibly P. Okay? We don't care what happens to P for a limit. And let me give a little bit more of an explanation. I'll write it down. Here's the idea. Idea of a limit. The limit as x goes to P of f of x equals to Q means f of x values can be made arbitrarily close to Q for all x values arbitrarily close to P except possibly P itself. We don't care what's happening to P for a limit of a function. Well, let's look at some examples in the xy plane. So as an example, the first one we'll look at is we'll define f of x to be 2 times the square root of x if x is greater than or equal to 0, and it's going to be 1 if x is greater than or equal to 0, and x is different than 1. And it's going to be equal to 1 if x is equal to 1. Okay? Then, let's draw a picture of this first. So here, when I go to draw this picture, 2 times square root of x, let's see. We let x be 0, we get out 0. We let x be 1, we get out 2. In this part, but we can't let x be 1. And if I let x be 4, we get out 4. It looks like this. Something like that. And then when x is equal to 1, we get 1 here. What I want to tell you, and the function continues on in this way, that the limit as x goes to 1 of this f of x, it is equal to 2. And the reason is that if you take any epsilon distance about 2, then if I come down here and get within this region of 1, all the points within this region of 1 are sent by f to points, y values, that are within this epsilon units of 2. Okay?
So you go above 2 by epsilon units, below 2 by epsilon units. That's true for all the guys this close to 1, except for 1 itself. Okay? And we don't care about that. And so that's why this limit is what it is. Okay? Let's look at another example. Example 2. Here, if we have f of x is equal to, very simple, what we have 2 times the square root of x if x is greater than or equal to 0 and x is greater than 1, then the limit as x goes to 1 f of x will be equal to 2. Okay? Here, I just not defining, f is defined at 1. Okay? Then a third example is if we let f of x be equal to minus 3x minus 7, then the limit as x goes to minus 3 here would be equal to, of f of x, will be equal to 2. And here we're thinking that f maps e, which is the real numbers, into r, so real numbers, and this is in those spaces r. We're going to have the usual metric, okay? That is the absolute value between x and y, x minus y. That's how absolute value is the distance between x and y. Okay, I'm going to prove part 3, third example. So I'm going to prove the limit as x goes to minus 3 of this particular function is equal to 2 in this setting. So the way we do this is we let epsilon be greater than 0 be given. I'm thinking of the definition here of what it means to be a limit. So what am I looking for? We need a delta bigger than 0 such that for all x in R with the distance, so here's absolute value, 0 less than absolute value of x minus 3 is less than delta, then the f of x values, let me write this down a little bit more generically here. So here, this would be the distance in the x, so here we would have x to minus 3 less than delta. Then the distance in y, which is still the same thing as x in real number, so I'll write down y, f of x, and here q, I'm going to write down what q is, we said it's 2, will be less than epsilon. Okay? So we want a delta bigger than 0 such that for all x element of R with 0 less than absolute value of x, here I'm going to write this x like this. Now this is a point, this is our space here, don't get those confused. X minus is a point. Minus 3 less than delta, then here this is the absolute value of f of x minus 2 is less than epsilon. So what we want is the absolute value of f of x minus 2 to be less than epsilon. Translating that into a little bit more specifics, we want, well, what's f of x? F of x is, its alpha value is like minus 3x minus 7. Okay? We want that minus 2 to be less than epsilon. So we want, here this is minus 3x minus 9 to be less than epsilon. I can factor out a minus 3, so we want minus 3 times x plus 3 to be less than epsilon. So we want absolute value of minus 3 times absolute value of x plus 3 to be less than epsilon. So we want, if you will, x minus a minus 3, that's absolute value of x plus 3, to be less than epsilon over 3, that's epsilon divided by absolute value. And so the delta that I need is sitting right there in front of me. Remember, essentially what we're trying to do is we're trying to control the output values distances from 2 here. We want that to be less than epsilon. And what we said was that was kind of equivalent to controlling the input values here, how close they are to minus 3. We need them to be within epsilon over 3 units. And I do get to control how close the input values are to p, which is minus 3 in this place, by letting delta be equal to something. Okay? So here it's clear delta should be epsilon over 3. Usually for me this is enough for proof that I've done right here, but I want to be very formal in this first case. And say, we're going to let delta equal to epsilon over 3. Then, for all x in R with 0 less than x plus 3 less than delta, we have the absolute value of x plus 3 is less than epsilon over 3. I'm just working backwards, which implies that 3 times absolute value of x plus 3 will be less than epsilon, implying minus 3x minus 9 will be less than epsilon, implying that minus 3x minus 7 minus 2 will be less than epsilon. And that implies, so for all x in R with 0 less than x minus 3, this says that f of x, that's f of x, minus 2 is less than epsilon. So the limit as x goes to minus 3 of f of x equals to 2. So I erased the board on this other side. I want to tell you that this class is an abstraction of things maybe we see in calculus. And here we're talking about limits of functions in an abstract setting. And we did a particular limit of a function in the real setting. It's not so abstract. And that's what we could do for a Cal 1 class, although most, or a lot of teachers do not include epsilon delta proofs in Cal 1, but some people do. But there's an example. I'd like to look at one more example. Okay. If we let f of x be defined in this piecewise manner, that it's 1 if x is greater than or equal to 0, and it's minus 1 if x is less than 0. Here's its picture. 1's here, looks like this. Minus 1's here, it looks like this. Then I just want to tell you that the limit as x goes to 0 of f of x does not exist. That's also DNE up here, my abbreviation. That means does not exist. And what's happening is that you can see that no matter what little region I put about 0, not including 0, the y values are going to be very far apart for certain input values within that region, no matter what little region I put here. So they aren't going to be close to one particular cube. Well, here's an important theorem. And in chapter 3, we learned about limits of sequences. And we're going to relate limits of functions to limits of sequences by this theorem. This is called the sequential criterion for function limits a lot of times I'll abbreviate that, the SCFL. And what it says is, we're going to start off with by letting X and Y be metric spaces. Okay. And E be a subset of X. And we're going to have F as a function. What's it going to do? It's going to map E into Y. So F maps E into Y. Okay. Then the limit as X goes to P of F of X equals to Q if and only if the limit as n goes to infinity of F of sub Pn equals to Q, and that's for every sequence P sub n in E such that P sub n is different from P, and that's true for all n element of J, and the limit as n goes to infinity of P sub n equals to P. Okay, so again, this is a theorem which relates limits of functions to limits of sequences. And it's an if and only if statement. So we'll go ahead and get started. Proof. So the general setup in both directions. Suppose X and Y are metric spaces here we're going to have E, a subset of X, and F maps E into X. One thing that's understood here that I didn't say, but that P has to be a limit point P for us to be talking about the limit of F of X as X goes to P. That's understood, by the way. It's understood from the definition of limit of a function, by our definition. So it's if and only if statement. That was the setup. So let's go the frontwards direction. Okay. Suppose the limit as as x goes to p of f of x equals q. Okay? And we're now going to show that every sequence that has certain qualities, a limit as n goes to infinity of f of that sequence has to equal q. So we're going to start off with letting p sub n be a sequence. In E, such that the limit as n goes to infinity of p sub n equals to p, and p sub n is different than p, and that's true for all n element of j. And we want to show that the limit as n goes to infinity of f of p sub n equals to q. Now f of p sub n is a sequence, and it's going to be a sequence in y. Okay? So that's what we want to do. Okay, how do I show a sequence in y converges to point in y? Well, we do this by using the definition. We let epsilon be greater than 0 be given. What we need an n, element of j, such that for all n bigger than or equal to this big N, the distance between, this is in y, of f of p sub n and q is going to be less than epsilon. That's what we need to have, is that big N. Well, the way we're going to get this big N is the fact that we know that p sub n converges to p. In part, anyway. That's going to be the N that works. Okay. But first, we know that since the limit as x goes to p of f of x equals to q, that's what we're assuming, and we've been given an epsilon, then there exists a delta bigger than 0, such that for all x in is E, with 0 less than the distance between x and p being less than delta, then that forces the distance in y. Let me make sure I know where we are. This is in x. Look, I'm going to write down little x here, distinction from this guy. Okay? This is little x. The distance between in y, between f of little x and q, will be less than epsilon. So what's this saying? Because of the limit of the function existing, that says as long as you're close enough to p, but not equal to p, then the output values will be very close to q. And we want output values to be very close to q, but not these output values necessarily, but the ones that are output values for the sequence p sub n. So since the limit as n goes to infinity of p sub n equals to p, then there exists an n element of j such that for all n bigger than or equal to j, look, I know if the input values are within delta units of p, the output values will be within epsilon units of q. I want the output values of the p sub n to be within epsilon units of q. So what I need to do is make sure that the input values, the p sub n values, are within delta units of p. Well, I can do that by, for all n bigger than or equal to n, I've written the wrong thing there. For all n bigger than or equal to n, the distance in x between p sub n and p will be less than delta. Okay? Since p sub n is always different than p, then for all n bigger than or equal to n, 0 is less than the distance between x and p sub n and p, which is less than delta, which implies, okay, since this input value is within delta units of p, that the output values their distance from Q will be less than epsilon. So let me write down the conclusionary statement for this part, this direction to prove. But we've got it. That's saying that the f of p sub n must converge. So the limit as n goes to infinity, f sub p sub n equals to q. And that's that part of the theorem. Okay, going in this direction, okay, to prove, I'm going to write up something wordy, in this direction, to prove that if for each sequence in E, let's call it P sub n. Let's say any sequence in E, P sub n, with P sub n being different than P, and the limit as n goes to infinity of p sub n equals to p implies f, the limit as n goes to infinity, f of p sub n equals to q, then the limit as n goes to infinity, the limit as x goes to p of f of x will equal to q. To show that direction, okay, we will prove the contrapositive. Okay? That is what we're going to do, and I'll write this down, is that we'll say, okay, we'll suppose that this is not happening, that the limit x goes to p of fx does not equal q. And then what we'll have to do is provide or create a sequence in p sub n that's never p, the limit of p sub n is p, but this doesn't happen. That the limit n goes to infinity, well, that infinity looks terrible. F of p sub n doesn't equal q. That's what we'll show. Okay, let me write that down, and then we'll do it. That is, we will prove that if the limit as n goes to infinity, no, it's x goes to p here, sorry, f of x is not q, then it is not true that every sequence in E whose terms are never P but yet converge to P. Imply that f of that sequence, I'll call it Pn, converges to Q. We'll show that that's not true. Okay? Okay. So let's go ahead and start on that task by supposing that the limit as x goes to P of f of x is different than Q. What does that mean? Well, that means there exists an epsilon naught greater than 0. So remember, it was for every epsilon. Oh, that's not true. So there exists an epsilon naught. Remember, for the definition, x goes to P of f of x equal to Q, that means for every epsilon. Okay, but it's not happening, so there exists epsilon. Such that for every delta you give me that's greater than 0, there exists an x in E with 0 is less than the distance between x and P is less than delta, but the distance between, oh gosh, this distance, let's back up. This distance here, that I wrote at the bottom of the board, it's with respect to this little x. It's with respect to the metric x. Okay? It's with respect to the metric x. Okay? But here, I'm going to talk about the distance between f of x, and that's in y, and q is going to be bigger than or equal to epsilon naught. That's what we have. Okay, so for delta equal to 1 over 1, following what we just said, there exists a x of 1 element of big X, such that 0 is less than the distance between x of 1 and P, which is less than this delta, delta sub 1 over 1, and the distance between in y, between f of x sub 1 and q is going to be greater than or equal to epsilon naught. Okay, that's true. So for delta sub 2 equal to 1 over, well, let's not call them deltas, just deltas. For delta equal to 1 over 2, there exists an x sub 2 element of x, such that 0 is going to be less than the distance between x sub 2 and p, which is going to be less than delta, which is 1/2, and delta sub y, the distance between f of x sub 1 and q, will be greater than or equal to epsilon naught. We just continue this process. Okay? So continue this process. To form a sequence. Okay, I call them x sub 1s. Well, all right. So I'm calling them x sub n's. N runs from 1 to infinity. And that's contained in E. Contained in E. Okay. Now let's talk about that sequence. Well, it's going to do what we want. In that since 0 is less than the distance between x of n and p, for all n, then that says that x of n is different from p. That's for all n element j. Also, since the distance between x of n and p will be less than 1 over n, then that will force the x of n's to converge to p. Okay, they're getting closer and closer to p. I can make that happen by, I can always choose an n to be less than any epsilon is given to me. Okay? But since the distance, here this distance was in x, the distance in y between f of x of n and q is always greater than or equal to this epsilon norm. They aren't arbitrarily getting close to, the f of x of n's aren't getting arbitrarily close to q. Then the limit, as n goes to infinity, of f of x of n is not q. And that's what we're wanting to do for the other direction. I'd like to list a corollary proof. Corollary, remember that's something that's a result from what we just did. And it has to do with the limits of functions. Function limits must be unique. If f has limit at p, then this limit is unique. So the proof. Look at the setup here. Let's let f go from e into y. Okay. Suppose the limit as x goes to p of f of x equals to q, and the limit as x goes to p of f of x equals to q prime. So it has a limit. I'm thinking maybe it has two of them. Maybe. Let x of n be a sequence any such that x of n is different than p for all n element of j, and the limit as n goes to infinity of x of n equals to p, then by the sequential criteria for function limits, okay, since this is a small s, we're still in the same sentence. Since the limit as x goes to p of f of x equals to q, what we have is the sequential criteria for function limits. The limit as n goes to infinity of f of x of n that's going to be equal to Q. Similarly, since limit as x goes to p of f of x equals to q prime by the sequential criteria for function limits, the limit as n goes to infinity of the same sequence, f of the same sequence, that's got to be equal to q prime. Now these are the same sequences. Oh, I made a mistake. This is a sequence. No, this is the same sequence. This sequence here and this sequence here are the same. This, f of this sequence, are the same sequences. And one of them goes to q and one of them goes to q prime. Since we've proven that limits of sequences are unique, then that says that q must be equal to q prime. And that's the proof. Okay, the next thing I want to do is make a definition. It's a very obvious definition about algebraic combinations of functions. So in particular, let's suppose this is going to be for complex functions. Suppose we have two complex functions f and g. Okay, what do we mean by complex? They grab input values and yield out output values that are complex values. They may grab input values that aren't complex values, okay? But what they output to are complex numbers. Both defined on E. Then, first thing we're going to define is f plus g acting on x. Well, that's going to be equal to f of x plus g of x. Similarly, f minus g acting on x is going to be equal to f of x minus g of x. F times g acting on x is going to be equal to f of x times g of x and finally f divided by g is a function that can be defined on x by f of x divided by g of x, provided g of x is different from 0. Okay, ladies and gentlemen, I'm going to end today with the theorem that we're just going to write up. We'll start there next time. And this theorem has 4 parts. We're just going to write it up. Here's what it says. Suppose E is a subset of X where X is a metric space. X is a metric space. P is a limit point of E. F and G are complex functions on E, and the limit as x goes to P of f of x, we give it exists, we call it A, and the limit as x goes to P of G of x, let's call it B, exists. Okay, then, here we got 4 parts. Part A is the limit as x goes to P of f plus G acting on x is equal to A plus B. So in this case, the limit of the sum of functions is the sum of the limits. Part B, the limit as x goes to P of f minus G acting on x is going to be equal to A minus B. Part C, right here, the limit is x goes to P of f times G acting on x equals to A times B. And D, the limit as x goes to P of f divided by G of x equals to A divided by B. And that's provided B is different from 0. B's got to be different from 0. And look, once we prove A, all the rest of them work very similarly. And it's going to be based on the sequential criteria for functional limit. Okay? And so we'll get to that next time. I thank you very much for your time and patience.